Okay, in this segment, we're going to consider a circuit configuration called the cascode. And this is a kind of a strange sounding word, and your spell checker is going to always try to autocorrect you to cascade when you try to type this. But cascode actually comes from a contraction of the phrase cascade to cathode. And this is a very old circuit configuration. It dates back to the vacuum tube days, where the cathode was one of the terminals on a vacuum tube, and they basically had two vacuum tubes connected in series. And in CMOS, the cascode configuration for an NMOS transistor looks like this. So it looks like a source follower in some ways. And in this case, we have V out. We've got some current I out. And then we have, instead of this being our input voltage, this is a voltage we're going to call the cascode bias voltage, VC. And we're going to call this the input voltage here, Vin. And this transistor MC, and this transistor we're going to call Min. So MC is called the cascode transistor. And Min is the transistor being cascoded. And this whole configuration is called a cascode configuration. Okay, so we can use the word cascode to refer to, as a noun, to refer to the whole configuration. We can use the word cascode as an adjective to describe the transistor here, the cascode transistor. And we can use it as a verb. We can say that this transistor is cascoding this transistor. And the basic idea of the cascode is, you can think of this as a source follower. Like I said, it is a source follower, where we are keeping the voltage on what would have been the input of the source follower fixed at VC, the cascode bias voltage. And of course, that basically means, since the source is going to follow what this voltage is doing, that the source is going to be held relatively fixed. Okay, so this is held relatively fixed. The basic idea is that the cascode transistor keeps the drain voltage, or the drain to source voltage of Min, basically more or less constant, despite potentially large changes in the actual output voltage. And we want to see what effect the presence of this extra transistor here, the cascode transistor, has on the incremental output resistance of this configuration relative to a single transistor, and also what effect it has on the transconductance gain of the circuit. In other words, if we were to change Vin by some delta Vin, how would delta I out to delta Vin change relative to what we would see for a single transistor? Okay, so our baseline for comparison is going to be a single transistor whose input is on the gate and whose output current is the channel current. So this is our baseline for comparison. Okay. So want to know, how does R out, which is delta V out to delta I out, compare and how does GM, which is delta I out to delta V in, compare between these two configurations. Okay, so the first one we're going to do is the GM. So of course the baseline is just going to be GM, little GM. Okay, so let's so here, so let's do the GM. So here for the baseline, we're going to apply our delta V in, and that's going to give rise to an I out plus delta I out, and it's just going to be delta I out is equal to little GM times delta V in, and so the GM of the circuit configuration is delta I out to delta V in, and that's just little GM. Okay, so that's the baseline. So for our cascode, let's put an early effect resistor in here. No. Yeah, let's put an early effect resistor in here. And let's put an early effect resistor in here. They're going to be the same. We're going to assume that these transistors are matched, so they also have the same current flowing through them under quiescent conditions, and so they should have the same RO. So when we add our, I'm going to assume for the purposes of our calculation here that the output voltage is being held fixed here, like we would in the GM phase of a node fixing calculation. And so when we apply our delta V into the cascode configuration here, that's going to create some current here, which we could call delta I. And that delta I is just going to be given, like it was down here, by the little GM of our input transistor times delta V in. But we want to know how much of that delta I gets to the output. Okay? Well, we're going to see a current divider, right? A two-way current divider. Some of that current is going to come from the RO, and some of it's going to come from above. And so we can call the amount that comes from above, let's say alpha times delta I, and the amount that comes from the RO is 1 minus alpha times delta I. Right, so we have it here, alpha being our current divider ratio, and we're interested in what fraction of the delta I makes it to the output. Right, so for our cascode, we have delta I out being given by GM times delta V in times our current divider ratio. What's our current divider ratio? Well, we have, we can express this in terms of the resistance, let's say the resistance of the opposite, well, let's do the conductance of the branch we care about divided by the sum of the branch conductances. Okay, and so the sum of the branch that we care about actually has two things in parallel with each other, right? So we have the GS of the cascode transistor, which is the same as the GS of the input transistor because they are matched, plus 1 over RO. That's the conductance of this RO, the RO of the cascode transistor, divided by the sum of all the branch conductances, which is GS plus 1 over RO, plus 1 over RO. All right, so that's the branch conductance of the second branch here. And so we can simplify this if we like. We can recognize that there's two 1 over ROs here. Right, so this is equal to GM times GS plus 1 over RO divided by GS plus 2 over RO. We can multiply top and bottom by RO. And that's going to be GM times GSRO plus 1 over GSRO plus 2 times delta Vn. Well, GSRO is much bigger than 1, so GSRO plus 1 over GSRO plus 2 is going to be approximately 1 because GSRO is much bigger than 1. And so the GM for the cascode is going to be delta I out over delta Vn, which is basically just little GM. This is the cascode configuration. And so the GM of the cascode is basically the same as the GM of the baseline. Okay, so it doesn't, the cascode transistor does not degrade the GM of the transistor relative to the transistor by itself. Okay, so for the R out part of the calculation, and take away our current increments here. What we're going to do is change the output voltage by a little delta V out and see how much current flows back in. And for the baseline, R out is basically just the early effect resistance, delta V out over delta I out. It's just the little RO. So this is the baseline. What about for the cascode? Well, the first time people see this, they will typically say, oh, well, we have these two ROs, they're in series. And so the R out should be is 2 RO. And that's actually not right. So if you thought that when you first saw this, that's totally fine. I did too, actually. But it's going to be actually different than that. And so to actually figure this out, what we're going to do is actually apply source splitting and superposition. Okay, so we're going to take this over here, connected to our voltage source here, and we're going to apply voltage source splitting. To get the change in I out. Okay, so we're going to take that output voltage source and we're going to split it into two pieces, one connected to the drain of our cascode transistor and one connected to the RO. want the total change in current flowing through both of these wires. So there's going to be an I out plus a delta I out here. And we're going to track the current increments here. So we're going to call this 1 and 2. And by superposition, we're going to consider the effect of each of these components of delta V out in turn. So we're going to first turn off the delta V out 2 and write down delta I out by superposition as the sum of 4 possible components. Okay, so here we're on replica source number 1. We're connected to the drain of the transistor, the cascode transistor, which is an ideal transistor. We're encapsulating the early effect on the cascode transistor in RO. And so we are accounting for it, but it's not on branch 1. And so delta I out 1, 1 will be 0 because branch 1 admits no current when we change the voltage on branch 1. And also branch 2 will not have any additional current flowing in it due to the change in voltage on branch 1 because that 0 current doesn't affect anything and the change in voltage here isn't seen by anything else. And so we've got 2 of the 4 components are going to be 0. And so we move on to branch 2 and apply our delta V out there. And here we're talking to an early effect resistor. And of course, the early effect resistor will change its current when we change the voltage on one side of it. And so there will be a delta I out 2, 2 due to that change in the voltage on branch 2. And that RO is going to be in series with whatever the incremental resistance is down here at node V. And that current will come out of this resistor, and it will see a current divider. Okay, now it sees a two-way current divider. There are 3 things connected down here, but we have the drain of the input transistor, which is ideal, and we have the RO of the input transistor, which we're accounting for by this early effect resistor here. And so some of it will go here, and some of it will go back up the cascode transistor and actually come out as a delta I out 1, 2. Okay, and so that will be basically a current divider. We can write that as a current divider ratio times delta I out 2, 2. Okay, so we're going to prefactor that out and write the delta I out as delta V out over the resistance of the incremental resistance of this branch, which we have as RO in series with the incremental resistance down here. Okay, the incremental resistance down here is going to be the 1 over the GS of the cascode transistor in parallel with RO, the RO of the input transistor. Okay, so this is delta I out 2, 2, and then we'll basically, that times 1 is the delta I out 2, 2, and then we're going to have the current divider ratio multiplying delta I out 2, 2 as giving us the delta I out 1, 2. And so the current divider ratio here we can express again as the conductance of the branch we care about, GS, divided by the sum of the 2 branch conductances, which is going to be GS plus 1 over RO. 1 over RO being the branch conductance of this branch down here. And so this is the current divider ratio delta I out 1, 2 divided by delta I out 2, 2. Okay, so these, when we multiply this through we distribute this first factor through the parentheses, we get basically delta I out 2, 2 and delta I out 1, 2. So we can do some things here. One is to note that because 1 over GS is a much smaller resistance than RO, this parallel combination is going to be dominated by the 1 over GS, and then when we add that in series with RO, that will be in turn dominated by the RO. So that this downstairs here is going to be basically just approximately RO. Second thing is when we put these over a common denominator, we can do that fairly easily. We get a GS plus 1 over RO minus GS. The GS's cancel upstairs. And we get downstairs GS plus 1 over RO. We can take the 1 over RO upstairs and use it to clear out the nested fractions downstairs. And we're going to get basically delta V out over, we'll just take it RO plus 1 over GS parallel RO. We get 1 over RO divided by GS plus 1 over RO. And then that means that R out, which is delta V out to delta I out, is just going to be 1 over the stuff that's multiplying delta V out, because we take this downstairs on this side, we take the delta I out downstairs on that side, we get basically RO plus 1 over GS parallel RO, and then taking this downstairs here and clearing out the nested fractions gives us a multiplier of GS RO plus 1. Well, we said that this is approximately 1 over GS, and then this whole thing is approximately just RO. And this whole thing here is basically just GS RO. Right? And these all follow because GS RO is much bigger than 1. And so the R out here is going to approximate down to GSRO times RO. So this is the cascode configuration. So I didn't combine these ROs here into GSRO squared because we have this RO up here. And so we find here that the incremental output resistance of the cascode structure is basically a factor of GSRO, the intrinsic gain of the cascode transistor, higher than the single transistor by itself. So if GSRO is a number like 100, that means that if we were to think about taking what would be the equivalent of a drain characteristic for this cascode configuration, we would find that in the analog of the saturation region, it is going to be something like 100 times flatter, 100 to 1,000 times flatter than the saturation characteristic of a normal transistor. And so far from being just a factor of 2 improvement, we get a factor of something like many tens to possibly several hundreds, which is a remarkable thing. Okay, so in this cascode configuration, we have a circuit configuration where the cascode transistor does not get in the way of the transconductance of the transistor, i.e. the transconductance is the same, but the incremental output resistance is drastically improved. Okay, and so if you think about the technique of calculating the gain of a circuit by node fixing, like we've been using, this suggests a way of greatly improving the gain of an amplifier. If we add cascode transistors to the output branch of the circuit, we would not affect negatively the transconductance part of the calculation. We would leave that basically unaltered, but we would vastly increase the output resistance. And so the product GM times R out would actually be improved by the factor by which we've improved R out. And so I guess I should have mentioned that we're assuming that these two transistors here are both operating in the saturation region. Okay, and so we need to ensure, in picking our cascode bias voltage, that this voltage V is at least a saturation voltage above ground. Or for a PMOS cascode, we would have to ensure that that intermediate node voltage is at least a saturation voltage below VDD. Okay, so that's important. And so if we take this idea and apply it to our current mirror differential amplifier, we get something called a Mirror-Cascode differential amplifier. And so we have our normal diff pair. We have our current mirrors. And there are several ways that we could arrange this. And I'm just basically showing you sort of the most straightforward way, or the least change to the circuit. So we have here 2 extra transistors in our output branch, one being a PMOS and one being an NMOS. So these are the 2 cascode transistors, and then we have our current mirror there, current mirror here. We can call this VCN and VCP. And if we think about kind of just simply adding these 2 transistors in series with the 2 output transistors, M4, we call them M4 and M8. When we imagine applying our delta, let's say delta VN here, or whatever, delta VDM, right? When that delta I1 gets mirrored by M3, M4, this PMOS cascode transistor doesn't get in the way and allows that current to go through unimpeded. Likewise, when the current's coming around the other way here, the NMOS cascode transistor doesn't get in the way of the delta I1 that's coming up and flowing to the output when we have the output voltage held fixed. But then when we look back into the output of the amplifier to probe its output resistance, we now see the parallel combination of the N cascode and the P cascode. And so it's going to be GSN RON times RON in parallel with GSP times ROP, and that's going to be a factor roughly of the intrinsic gain. It's actually bigger by a factor of the parallel combination of the intrinsic gain of the N and the P cascode transistors. But it's going to be something like on the order of an improvement by a factor of, let's say, 100 or a few hundred. And that's going to take us from something that's like the gain of the whole amplifier being the intrinsic gain of one transistor to the product of the intrinsic gain of a transistor and another transistor. And so we go for from something like 40 dB gain, factor of 100 for our single stage amplifier, to something like a gain of something like 80 dBs, which is 40 plus 40, or 10,000, just by adding these 2 transistors. Now I haven't said how we would generate these VCN and VCP bias voltages. We have to maintain, we basically want to pick VCN so that this intermediate node is about 1 VDS sat above ground. And we would like to pick VCP so that this voltage here is about 1 VSD set below VDD. Because we need both of these transistors to be operating in saturation in order for the enhanced output resistance to be true. And so as Vout starts either swinging toward VDD or swinging toward ground, basically we want, let's say, the cascode transistor to fall out of saturation at the same time as this transistor does. If we have, let's say, VCN set too high so that this voltage here is substantially above 1 saturation voltage above ground, then as soon as Vout gets within a saturation voltage of wherever that is, then the cascode transistor starts falling out of saturation, and it's in its ohmic region. And then as we move Vout down further, this node is going to go with it, and we're going to be moving along the drain characteristic of this transistor, and we're just going to have the ordinary RO of this transistor, and the cascode might as well not even be there. Right, so we would then, under those circumstances, want to push VCN lower so that this voltage moves down, and the optimal place that we would want this voltage to be is just one saturation voltage above ground, so that Vout will swing all the way down to basically 2 VDS sat before both transistors start falling out of saturation at the same time. Okay, so the gain ADM for this circuit, just recapping, is going to be delta Vout over delta VDM. And that's going to be basically the GM of the NMOS diff pair times GSN RON squared parallel GSP ROP squared, where these are from the output transistors, and this is from the diff pair. Of course, if they're all basically operating at the same current levels and they are matched, then the GSN and the GMN of the transistors in the different parts of the circuit will be basically the same. Okay, so this is one way of achieving a higher gain with the kind of circuit we've been talking about without resorting to cascading multiple stages and getting gain by cascade. So we have an option of cascoding or cascading to get improved gain. Okay, so I think that's probably all I'm going to talk about right now, because getting into something else would take us probably into a longer video than I would like to make this one. So we will pick it up here next time.